This lecture is about amortized complexity analysis. It's a type of analysis that we need to understand the performance of some advanced data structures, particularly the Fibonacci heap, which we'll be looking at in the next lecture. First of all, let's explain why we want a concept of amortized analysis. Here's a definition to start off with. Aggregate analysis simply means work out the total cost of a sequence of operations. So what's this about? Why do we draw attention to this idea? Let's work with an example. Remember Dijkstra's algorithm. Dijkstra's algorithm was an algorithm for finding shortest path in a graph. And the algorithm that we used, that Dijkstra devised, uses a priority queue to decide which vertices to visit. How does it use the priority queue? Well, it keeps track of a set of vertices that are waiting to be explored, and for each vertex it stores the distance that is computed from the start to that vertex. And the algorithm, Dijkstra's algorithm, repeatedly picks out the next vertex with the smallest distance with an operation popmin, and we argued that it makes up to v calls to popmin. It also has operations to add new vertices to the priority queue or to decrease the key of an existing element, and we argued that it makes O of e calls up to one call per edge in the graph to those two operations. So Dijkstra's algorithm uses a priority queue to decide what to explore, and in one pass of Dijkstra's algorithm it will make up to v calls to popmin, and it will make up to e calls to push or decrease key. So the total running time of Dijkstra's algorithm is this expression here, v times cost of popmin plus e times cost of push or decrease key. When we're analyzing the complexity of running Dijkstra's algorithm, we don't care how much one of those individual operations costs. We only care about the total cost of v popmins and e of the others. And if it so happens that we can organize our data structure in such a way that one of the early calls is very expensive because it sets up some useful structure which will be useful later on, and this means that we can make our later calls very cheap, then it's a good thing to do as far as aggregate analysis is concerned. Very often when we're analyzing advanced algorithms, that's all we care about. We care about a total collection of operations which need to be done together to achieve the single task. Now, to make it easier for us to reason about these aggregate analyses, it's useful to make another definition, the definition of amortized cost. If the true costs for a sequence of operations are C1, C2 up to CK, I'm imagining here a sequence of k operations, each with their own true cost, and I invent some fictitious costs C1 prime, C2 prime up to CK prime with the following property, with the property that C1 less than or equal to C1 prime, C1 plus C2 less than or equal to C1 prime plus C2 prime, and so on, all the way C1 plus CK less than or equal to C1 prime plus ... plus CK prime. Then these costs, C1 prime up to CK prime, are called amortized costs. Let's just rewrite it in more intuitive language. What this collection of equations really says, it says that for any sequence of operations, the aggregate true cost, simply the sum of C1 up to CK, is less than or equal to the aggregate amortized cost. And this equation, which says aggregate true cost less than or equal to aggregate amortized cost, this is an equation which holds true for the first operation, it holds true for the sequence of 2 operations, it holds for the sequence of 3 operations, ... This equation, this fundamental inequality, has to hold for any sequence of operations, no matter how long. This is the fundamental defining equation of amortized costs. Amortized costs are just an accounting trick, a different way to ascribe the cost of an operation. Let's just have a look at the concept of amortized cost in more day-to-day accounting. Let's imagine that I'm buying a fridge. The typical cost of buying a fridge, let's say £450. When you buy a fridge, you know it will have to be disposed of eventually, and the going rate for getting rid of a fridge in an environmentally friendly way, around £80. Okay, so I could treat it as I buy a fridge, it costs me £450. Later on I have to dispose of the fridge, it costs me £80. Alternatively, I could simply say I'm going to spend £530 up front. £450 will go to the shopkeeper, £80 I'll put into a bank account so that when it comes time to dispose of the fridge, I have the £80 in my bank account. I've paid everything I need to. I haven't changed the cost of any of the operations here. I've simply said I will have to pay a total of £530. For accounting purposes, I might as well treat that all up front, because actually buying a fridge implies that I will have to pay to dispose of it downstream. That's a totally arbitrary way to account for the costs. I could say, for example, I'll pay £490 up front and then pay the remaining £40 when it comes time to dispose of the fridge. It makes no difference. The only thing that truly matters here is that if we call this one C1 and C2, C1 prime, C2 prime, the definition of amortized cost requires C1 less than or equal to C1 prime. Okay, that's another way of saying that the amount of money I budget in the first instance has to be enough to pay for the fridge itself. That's common sense. Secondly, C1 plus C2 less than or equal to C1 prime plus C2 prime. The accounting scheme must allocate enough total money to pay for those operations. Alright, so that's the abstract definition of amortized costs. Here's what amortized cost looks like in practice when we're looking at an algorithmic problem. If you read something like this data structure supports push at amortized cost O of 1 and popmin at amortized cost O of log n, where n is the number of elements stored. This is the sort of thing you might read in a textbook. When you read that, what it really means is a statement about aggregate costs. Our fundamental defining equation, remember, aggregate total cost of any sequence of operations has to be less than or equal to aggregate amortized cost. So, what does that mean in the context of this data structure? It means that if we take any sequence of operations, for example, if we say we'll do n1 push operations and n2 popmin operations, then the total true cost, the aggregate true cost, is less than or equal to the aggregate amortized cost. Aggregate amortized cost, I've got n1 copies of push, which has cost O of 1. I do n2 operations which are popmin, which has cost O of log n. So in other words, my aggregate true cost less than or equal to my aggregate amortized cost, and I can just simplify the algebra on the right hand side to give me O of n1 plus n2 log n. That's all that amortized cost is saying. Amortized cost is only ever saying aggregate true cost less than or equal to aggregate amortized cost for any sequence of operations. Just one little note about the big O notation on this slide. I've said amortized analysis should apply to any sequence of operations no matter how long. So I want this equation to hold if n1 is small, if n2 is small, the equation has to hold. If n1 is large, if n2 is small, it has to hold, and so on. So what do I mean when I have big O in this equation? I'm thinking of the big O as applying to some other size of the problem. I'm thinking here what the problem text suggests is that the big O means asymptotic in n, the size of the problem, the size of the data structure. When we look at amortized analysis, when we look at aggregate analysis, we are talking about arbitrary sequences of operations of arbitrary length, whether it's small length or large length. And if there's a big O in there, the big O must be referring to some other aspect of the problem. So we've said amortized cost is just some accounting trick. It's some totally arbitrary way to reassign the costs of a sequence of operations subject to the fundamental equation here. How do we invent accounting costs? How do we invent amortized costs? There is a systematic way, a useful, simple trick, and let me write out the abstract definition of that trick. A general purpose method for producing amortized costs is called the potential method, and it's defined like this. Given a function, we'll call it the potential function phi, and phi will be a function which will take any possible state of the data structure and map any possible state to a real number above or equal to 0. This is potential in the sense that physicists use the word potential. Physicists talk about potential energy and so on. The potential of a state is a measure of how much energy is inherent in that state. Intuitively, I want to think of phi as measuring mess. What we're going to be looking at in advanced data structures is a variety of clever algorithms which in some sense they can accumulate mess as they're running. Every now and then we'll clean up the mess. We'll do a big expensive tidying up operation and that will cut down the amount of stored up mess. Okay, so given the potential function phi, which will make the following definition, I'm going to define C prime, the amortized cost of an operation, to be equal to C, the true cost of the operation, plus phi, the potential applied to the state of the data structure after, I'll call that S post to refer to the state of the data structure after the operation has been performed, minus phi, the potential applied to S ante, by which I mean the state of the data structure prior to applying the operation. So if we're thinking of phi as measuring stored up mess, if the operation increases mess, in other words, if phi afterwards is higher than phi beforehand, that will mean that C prime is larger than C, the amortized cost is larger than the true cost. If the operation decreases the amount of stored up mess, then C prime will be less than C. So you can see that this idea of a potential, measuring the amount of mess in the data structure, is basically a way of penalizing messy operations. If I'm an operation and I increase the mess in the data structure, I will be assigned a cost larger than my actual true cost. So this is just a definition of amortized cost. It's a definition of a variable C prime. What we actually need to show is that this notion of amortized cost satisfies the fundamental equation. Remember, the fundamental equation says the aggregate true cost is less than or equal to the aggregate amortized cost for any sequence of operations. So that's what we actually need to prove. Let's write out the question. We need to prove for any sequence of operations. Let's write out the sequence of operations saying, let's imagine there's some initial state S0. We do operation 1 which has cost C1. That takes us to state S1. We do operation 2 which has cost C2. ... And then finally CK, operation K takes us to state SK. So we need to prove that for any sequence of operations, the aggregate true cost is less than or equal to the aggregate amortized cost. That's the definition of amortized cost. I've proposed a C prime. I need to argue that C prime is indeed a legitimate concept for amortized cost. So let's just work this out. I'm going to start off with the right-hand side. The aggregate amortized cost of this sequence of operations. I'm just going to sum up the terms. C1 prime plus C2 prime plus ... plus CK prime, which is, using the definition, this is equal to C1 plus potential associated with state S1 minus potential associated with state S0 plus amortized cost of operation 2, C2 plus potential phi associated with state S2 minus potential phi associated with state S1 plus ... plus CK plus phi of SK minus phi of SK minus 1. Okay, so let's first of all gather up the terms. I've got the true costs, C1 plus ... plus CK. And then there's a neat telescoping trick. Here I've got plus phi of S1 minus phi of S1. I'll have plus phi of S2 minus something in the middle ... and the plus phi of SK minus 1 minus phi of SK minus 1. All of these potentials, all of the phi's cancel out except for the very start and end, leaving me with minus phi of S0 plus phi of SK. So let's just rewrite that. I'm going to rearrange it. I'm going to put the true costs on the left-hand side, the C1 plus ... plus CK. So in other words, the aggregate true cost is equal to aggregate amortized cost plus phi associated with the initial state S0 minus phi associated with the terminal state SK. Okay, that's what we obtained. We obtained this equation just through simple algebra. Two more facts to bring in, or one fact and one definition. We have defined phi to be above or equal to 0. Therefore, phi of SK is above or equal to 0. That's just something we're going to insist on whenever we define a potential function. And another thing we're going to insist on is we shall assume that phi applied to an empty data structure is equal to 0. So, in other words, for any sequence of operations starting from an empty data structure, what we've proved is that the aggregate true cost is equal to aggregate amortized cost plus 0 minus something positive. In other words, this is less than or equal to the aggregate amortized cost. So, in other words, this C prime, which I proposed here via the potential function, is a legitimate amortized cost. It satisfies this basic inequality. Let's work through a practical application of the potential method to see how this formal definition works in practice. See how you actually solve real problems. The problem I'm going to look at is a dynamically sized array. A dynamically sized array is, for example, what Java uses to store an array. Initially, we might start off with an empty array, let's say with capacity 1. Let's imagine we append an element. It's got available capacity, it just writes the element into that slot. Let's suppose we call append again. There's no space to write a new element into that slot, so what it does first of all is it creates a new array of size 2, new array of capacity 2. It copies that one element that we had before into the new array, and it writes in the new element. Let's imagine doing another append operation. As before, it figures out there's no space to append to write in the new element. So first of all, it will create a new fixed size array of size 4. It will copy across the existing 2 elements, and then it will write in the 3rd element. Next time we call append, it's easy. All we need to do is write in the new element into the 4th slot of the array. If we call append once more, we have to first of all create a new array of size 8. We have to copy those 4 elements into the array of size 8, and then we can have space to write in the 5th element. And if we call append once more, well, there's available space this time, so we just write it in. So in general, the cost of an operation is 1 to write in the element, plus the number of items which have to be copied across in the event that we have to double. So let's just write out what the costs are. For this first append, the cost is 1. We simply write in the element. For this second append, the cost is 1 to write in the element, plus 1 because we had to copy across the old element into the new array of size 2. Here, next operation cost is 1 to write in the new 3rd element, plus 2 because we copied across an array of size 2 into this new array. This next append has cost equal 1. It's just writing in an element. This has cost 1 to write in the element, plus 4 because we have to copy 4 elements across into the new array. This last append simply has cost 1. Okay, so this is looking at the costs of each of the individual operations. Let's try and analyze the amortized complexity of these operations using the potential method. So I'm going to invent out of thin air a potential function, and the potential function that I'm going to invent will be phi equal twice times number of items in array minus the capacity of the array. Where did I invent this potential function from? Well, we'll look at some examples of potential functions and we'll get more and more experience. So in a few lectures' time, we'll be in a position to ask how do we go about designing potential functions for new problems. But for now, I want you to just take this as a given potential function which I'm going to arbitrarily invent. So let's go ahead and work out the potential associated with each of these states. For this state, phi is equal to twice the number of items in the array, 2 times 1, minus the capacity, which is 1. For the second state, phi is equal to 2 times the number of items in the array, which is 2, minus capacity, so we're left with potential 2. Okay, so these are the costs and the potentials. Now let's work out the amortized cost of each of the operations. I'm actually going to start with this one. Amortized cost. Amortized cost is just true cost plus change in potential. True cost is equal to 2. Change in potential is new potential is 2, old potential is 1, so the change in potential is plus 1. So my total amortized cost is equal to 3. Next step, amortized cost. True cost, which is 3, plus change in potential. New potential is 2 minus the old potential, which is 2, so I'm left with 3. Okay, so what we've found is that the amortized cost turns out to be a constant for all of these operations. If you're eagle-eyed, you'll have noticed that I skipped the first state. There's a slight problem here. What's the potential for the initial state? The potential is twice the number of items in the array, which is 0, minus the capacity of the array, which is 1, which is a negative number, which violates what we needed the potential to be. We needed the potential to always be positive, and we needed the potential to be 0 for the initial empty state. So this is a bit of a mess. I'm going to just kludge to get rid of that problem. And the kludge that I'm going to do is I'm going to say, take the positive part of this. In other words, if the formula twice number of items minus capacity is positive, I'll just use it. If it's negative, I'll take the max of that with 0. So I'm going to say the potential here is 0 for my initial state. That's just a kludge to force my potential function phi to suit the requirements. And you can go through and just check this small change here I made to enforce that it's non-negative doesn't change any of the potentials which I've written down in green. And we'll just work out here the amortized cost of this very first operation is true cost is 1 plus change in potential 1 minus 0. So we've got amortized cost of 2 for this operation. If you're trying to work through a problem of this sort, I'd recommend similar reasoning. Work through the general case, and then if you find you need to do some little tweaks to ensure that phi is always positive or that phi is initially 0, just do the tweaks at the end and then double check that it hasn't messed up any of your later calculations. Okay, so this is just working through by hand a very concrete example. Let's write out the general calculation that we're doing here. The cost of an append operation, if we need to expand the array, if we need to expand capacity, let's say the true cost is, on the previous slide I said 1 plus n. Let me be a bit more general here. I'm going to write O of 1 plus O of n. When we think about costs, we normally like to use this big O notation because we don't really care about multiples and small constants and so on. So I'm going to say the true cost is O of n. Let's work out the change in potential. Let's imagine that we needed to expand the array from size n If there were n items in there, the old potential would have been 2 times the number of items minus capacity, 2n minus n. So the old potential is n. The new potential, I've got to copy across all those n items, and I'm going to double capacity, and there'll be one new item in there. So the new potential is twice times the number of items, 2n plus 1, minus the capacity, 2n. So I'm left with potential 2. So the total cost, the amortized cost, is the true cost, O of n, plus change in potential, plus new potential minus old potential, which is equal to O of 1, because the n work and the minus n change in potential cancel each other out. What about the other case? The cost of append, if we don't need to expand capacity, the true cost is O of 1, simply to write in the new element, and the change in potential, remember potential is twice times number of items minus capacity. We're not changing the capacity at all, so the change in potential is just plus 2 to reflect the fact that we've got one more item. And if we add these two together, the amortized cost is O of 1 plus 2, which is just again O of 1. Okay, so what we've argued here is in all cases the amortized cost of an append operation is O of 1. This is what a typical amortized analysis looks like using the potential method. I hope it looks a little bit strange, or at least it looks a bit strange the first time round we look at it. When you see an expression like this, O of n plus 2 minus n, what does that even mean? Let's have a much more careful look at what's going on behind this calculation. Let's have another look at this amortized complexity analysis just to make sure that we're not pulling any tricks. This is exactly the same maths that I wrote out on the previous slide. Let's just recap. We defined the potential to be twice times the number of items in the array minus the capacity of the array. And we said, what's the cost of an append operation if we do need to expand the array? We said, if we need to expand from size n to 2n, then the true cost of this expansion is O of n, and the change in potential delta phi is 2 minus n. And we added those together to come up with the answer O of 1. So how does that actually work? Well, if in doubt, go back to definitions. Here's the definition of big O notation. Whenever we use big O notation, we mean something like this. True cost equal big O of n means there exists an n naught and a constant kappa, such that for n larger than or equal to n naught, the true cost of this array operation is less than or equal to kappa times n. This is just the straightforward definition of big O notation. Similarly, for the O of 1, there's a different constant n naught prime and a different constant kappa prime, such that for n larger than or equal to n naught prime, the true cost of this operation here is less than or equal to kappa prime. And now let me actually modify my definition of potential. Instead of saying phi is twice number of items minus capacity, I'm going to multiply it. And I'm going to choose the multiplier max of kappa, kappa prime. I'm going to choose that multiplier big enough that it can cancel out the two big O notations. So let's just follow through how that works. The change in potential is now 2 minus n times the maximum of kappa and kappa prime, using our modified definition of potential. So when I add these two together, I've said true cost less than or equal to kappa n, so the amortized cost must be less than or equal to kappa n from the true cost, plus the modified change in potential term, and if we add these two together we get less than or equal to twice times a constant. So now you can see why I multiplied my potential. I multiplied my potential up by just enough to compensate for the unknown constant involved in the big O notation. Same trick applies in the other situation. The true cost is O of 1. The change in potential is twice times maximum of kappa, kappa prime. If I unpack the big O notation, it tells me that the true cost of the operation is less than or equal to kappa prime. And so for n sufficiently large, the amortized cost is less than or equal to, amortized cost is equal to true cost, and we've said true cost is less than or equal to kappa prime, and we've also got a 2 times a constant from the change in potential. So what we've said that in both cases, if I choose n sufficiently large, if I make n bigger than max of n naught and n naught prime, those two constants, if I make my n sufficiently large, then the amortized cost, in the first case it's less than or equal to 2 times the maximum of kappa and kappa prime. The second case it's less than or equal to kappa prime plus the same thing. So I have amortized cost less than or equal to something or other to do with the constants, which is just another constant. I could call it kappa prime prime. So for n larger than or equal to n naught prime prime, the amortized cost is less than or equal to some constant kappa prime prime. Now, I recommend you don't go through this sort of fiddly, meticulous calculation every time, it's a good idea to do it once or twice to reassure you that there are no hidden tricks being swept under the carpet with the big O notation. Let's just finish up with another interpretation of what we were doing with this dynamically sized array. I've written out the steps involved in building up this array. I've written them out slightly differently. I've separated out the append from the doubling of capacity that it requires. So if I want to append an item and I have to double capacity, I'm going to write that as two steps. Firstly, double capacity and then do the append. Likewise, this append here required a doubling of capacity and this append required its own doubling of capacity and so on. The whole point of amortized analysis is if there's work that needs to be done, let's not get hung up about who we pin that cost on. It's just work which has to be done, which will go into the aggregate analysis. So now let me look at the change in potential involved with all of these operations. I'll start partway through because, as we said, the initial case is just slightly different. The append here, the append operation simply writes in a new element, and according to the definition of potential, delta phi will be equal to +2 because we're increasing its concept of messiness. The doubling of capacity, if we look at that as a step on its own, we're doubling capacity, we're copying two items across. The cost is equal to 2, and the change in potential, based on the potential function we invented, is equal to -2. The next append, there's a change in potential of +2, and then another change in potential of +2. And then when we next need to double the capacity, the cost of this doubling of capacity is equal to 4 because there are 4 elements to copy across, and the change in potential is equal to -4. So what you can see is going on here is that there's a bunch of operations which build up potential, and then an expensive operation and a decrease in potential. And we've arranged things perfectly so that the build-up of potential totally pays for the expensive cost of the cleanup operation. Build up potential. And what we're doing here is we're using the stored potential to pay for the big tidy up, the big cleanup operation. So that's the picture of potential to have in your mind. When you increase potential, think of it as putting some money aside in a bank account so that when there's an expensive operation later on, you pay for the expensive operation by paying out money from your bank account. So here phi is basically measuring how much money you're setting aside in the bank account. Let's finish off with a brief discussion of what makes a good potential function. What we've learned so far is how to compute amortized costs given a potential function. But this leaves the question of, have we found the best potential function we could? In other words, how much effort should we put into trying to improve our potential function so as to end up with lower amortized costs? Here's an example exercise. The exercise says, consider a binomial heap which supports operations push, decrease key, and popmin. The binomial heap we'll study in the next lecture. The exercise might say, using the potential method, in other words, you have to invent your own potential function, show that in a heap with n items, the amortized cost of push is O of 1, the amortized cost of decrease key is O of log n, the amortized cost of popmin is O of log n. Okay, so we just have to go away and be clever and invent a potential function which leads to those costs. But then part B of the question says, construct a sequence consisting of n1 push, n2 decrease key, and n3 popmin operations whose total cost is this function big omega of n1 plus n2 log n1 plus n3 log n1. Why did we choose that? Well, we know that for any sequence consisting of n1 pushes, n2 decrease keys, and n3 pop mins, the total cost is big O of n1 plus n2 log n plus n3 log n. Here n is the maximum number of items in the heap. Obviously n is less than or equal to n1. n1 is the number of items we've pushed in, so instead of n I'm going to write n1 in this expression. So for any possible sequence of n1 push, n2 decrease key, and n3 pop min, the total cost is big O of this expression here. The question is asking us to prove that there exists some sequence whose cost is lower bounded by exactly the same expression. And if we have these two, if we have a matching upper and lower bound, that tells us that it's impossible to do better. If someone came along and told you that they had discovered that the amortized cost of push is O of 1, the amortized cost of decrease key is O of 1, and the amortized cost of pop min is O of log n, if they tried to tell you they had discovered that, you could answer them and say, no, that's impossible. Look at my lower bound. I have a sequence which costs more than what you're claiming. So if you can construct a matching lower bound, you know you have invented the best possible potential function.